in the previous class, we will start off just trying to recall what we did. On a suddenly started plate, this is what we did. We said that there is a plate which is suddenly moved at velocity u. Before that, it was stationary. And then you have fluid here, which is all stationary. And then after some time, the fluid will start experiencing this motion. So this is the type of velocity profile that we expect to get. And we saw that the velocity is given as u times 1 minus error function of zeta, where zeta was y upon square root of 2 nu t. Okay. And we saw that if we have to define, and this was a last problem, last question in the midsem, which was to sort of see that what is this thickness, and we said that this thickness can be defined as, let us say, 5% of the point where the velocity becomes 5% of the plate velocity. So it's like this becomes equal to, or if I have to divide it by this, so this becomes 0.05. So it is going to correspond to certain location, certain value of eta, which is going to satisfy this relationship. And that value of eta is 1.38. So then that means that this is now y becomes like delta. So if I have to say delta is equal to 2.76 times the square root of nu t. And we said that this is the typical diffusion behavior because this delta is increasing with time as a square root of t. Okay, so this is the diffusion like behavior, t to the power of half. So whenever you see t to the power of half, we tend to think of that as a diffusion dominated flow. That's the diffusion part. And it comes from this basic understanding, and that's why this problem is so important. And the second question that was to sort of see that whether you have understood that this nu is encompassing both viscosity and density. So it is dependent on both these two things, both these two fluid parameters. So if you change either of them, the viscosity, the kinematic viscosity is going to change, and that is going to change the diffusion time. Okay, and it's a simple solution, 1 to 100. So that square root of that will be 10. So, and it is increasing. So the viscosity, this viscosity is increasing, this nu is increasing. So the diffusion time will increase by a factor of 10 in a square root manner. That's essentially all there was to it in the second part. So it's like a giveaway question that was given. I mean, assuming that you have followed whatever was done in the class, and you, even if you would sort of remember that's 1.38, which was mentioned towards the end of the previous class. Okay, so this is where we left, and this is, as we said, the Stokes' first problem. And the importance of this problem is that it gives us an idea of how fast this information is diffusing in the flow. And the similar thing you can say with thermal diffusion. So if you have a plate which is heated and you want to see how fast the heat travels, it is again the same problem. Okay, so instead of nu, you will have alpha there, thermal diffusivity. And that's where essentially the word diffusivity is coming in. Okay, so nu, we think of diffusivity. Diffusivity essentially means it is how fast things are diffusing. And this is one problem which gives you a very clear idea of how fast things are diffusing. Okay, momentum is diffusing here. Okay, and just to sort of further emphasize this point, this is momentum diffusivity. If you look at it dimensionally, what is the dimensions of nu here? Meter square per second. So I hope you sort of, and why this is sort of little bit interesting, because if you look at density, it has kgs here, we have some kgs here, okay, something. But what is important is that this kg cancels out, okay, and you are only left with meters and seconds. Okay, so then there you can see that the word kinematic is used to sort of emphasize the point, the fact that there is no mass term in there. Okay, it's only there is no kg in there. So that's where the kinematic term comes in. So these were the 2-3 remarks that I could not make before the closure of the previous class. So that's where we are starting from. And today what we are going to do is look at the Stokes' second problem. So this problem is going to be very similar to whatever we have seen earlier, but with some differences as well. So here what we are saying is that we take this plate, like whatever we had earlier. Now we are going to, instead of suddenly moving it, we are oscillating it. So here it is, I'm giving a u cos omega t. This is the way in which the plate is going to be moving, so it's or rather oscillating. So there is one cos component which is just oscillating this plate. And our interest is the same. How does the solution look like? So at some distance, again we can say this is my x distance, this is my y component of velocity, sorry, y direction, this is my x direction. I can fix it any arbitrary point because it's a large plate, so that's like my center. Okay, because it's infinitely large, I can think of anywhere. And so what do you sort of expect? First, maybe what we will do is this will have certain differences with respect to the previous problem in terms of how the solution would look like. Maybe we can start off by writing out the governing equation so that you know what we are talking about. So what is the governing equation here, and how was that obtained? The governing equation was obtained by saying that the plate is very large along the x direction, and therefore there are no gradients along the x direction. Dou u dou x was 0, and because of which we went to the continuity equation, we found that dou v dou y is equal to 0, and because v is equal to 0 at the plate, it should be 0 throughout. Okay, so once we have that, then we say that in the momentum equation, in the y momentum equation, all velocity terms are 0 other than pressure, so that gives me dou p dou y is equal to 0. Okay, so that means there is no pressure gradient along the y direction, and we are saying that there is no pressure which is imposed along the x direction. This was done under the assumption that there is no dp dx which is imposed on it. Okay, so then the pressure is constant throughout, so I don't have to worry about pressure, I don't have to worry about v, which is 0 throughout, and we are left with only one equation and one variable, which is my u, and that variable is and that equation is this. So it is dou u or dou t. That's the only term that survives from the left hand side, and is equal to nu times dou 2u dou y2. So this is the governing equation that we had earlier, and you can see that the problem has not changed in terms of how it is set up. So therefore, the governing equation should not change. Now, why should the solution change? Is because the boundary conditions have been changed here. Okay, so if you change, and that tells you again, this is a simple situation where we are looking at two different problems, same set of governing equation, but very different solutions, and these solutions are different because the boundary conditions are very different. So this is just to sort of emphasize the fact that the solution changes if the governing equation changes, which is obvious, or even if the boundary condition changes, then also there is a strong change that will have a strong impact on the solution that you are going to get. Okay, so this is the solution, and again, why is this dou u dou t term is going to be there? That is obvious because you are changing something at the wall here, and therefore should be changed. I mean, the behavior should be a function of time. And of course, this is, in some sense, you have already said it's like a diffusion part. It is already telling us how far this information is going to go. So that's the sort of the very sort of a simple setup that we have. And here, when I look at the problem, okay, now first, how did we solve this problem? We impose some sort of a similarity, right? So what was the condition for similarity? So similarity variable, this eta is my similarity variable, y upon square root of t, square root of nu t, that's my similarity variable, right? And what we said by similarity is that instead of having this is u is a function of y and t, so it's very clear that u is a function of y and t. So there are two independent variables, y and t, but by similarity we mean that there are no two independent variables, but there is a single variable which is governing the behavior, which is essentially y upon square root of mu t. Okay, so this is my similarity variable that we had earlier. Okay, not here. So under what condition is this applicable? So I don't know, did we talk about that? Under what conditions can we find similarity solution? So similarity solution we can find when there is no imposed length scale or there is no imposed time scale on the problem. Okay, and what do we mean by that? So we can maybe, again, I'm just going back to this problem, and maybe I will explain to you how can we impose a velocity scale? How do we impose a time scale? And then once you understand that, you will understand the other part when there is nothing which is imposed on it. So let us say I look at this problem, and let us say that there is, so right now, good thing is that this is infinite depth. So that means that there is no length scale now. Now, how do I impose a length scale? What do we mean by that? I would say that there is fluid 1 here, and there is fluid 2 here. Okay, now if there is fluid 1 and fluid 2, what have I done? You will immediately have to ask me how far is this plate, what is this depth? Okay, maybe this is infinite still, but what is the depth of this fluid 1? Okay, so you can see that this length scale is now coming to the picture, L. Okay, so I have to, now my solution is no longer going to satisfy the similarity. Similarity will not work for you, right? And how did we find that similarity is working? Again, from the previous problem. So again, the previous problem in the solution wise looks very simple, but there are a lot of intricacies which were involved. So how did we know that it was working? Because we found that there were three conditions. This equation needs three conditions for satisfy two boundary conditions and one initial condition. There are three conditions that needs to be satisfied, but we could transform that equation into a second order equation which requires only two conditions, and we said that there should not have been any contradiction when in the boundary conditions, in the conditions that the equation should not satisfy. Okay, and we saw that automatically the conditions, three conditions got folded into two conditions automatically. Two conditions essentially became the same. Okay, so that is like a check to sort of say that similarity is working for us. Whereas if you do the same thing here, okay, in principle everything is very similar. Again, only differences in terms of the boundary conditions. At the boundary now, what condition would you apply? I gave you as a hint in the homework, not in the homework, but the mid-sem. Continuity of velocity, continuity of shear stress. Okay, so those are the conditions that you will have to imply. So that's how the motion from one layer is now going to be transmitted to the next layer. Okay, so that is, now you can see that here I've imposed a length scale. Okay, now what the other thing that length scale I can impose is by saying that this plate has a finite size. If I say that this plate has a length scale L, not infinity, then you can say I have imposed a length scale. Okay, so you can see that when you do that, you will not be able to find similarity solution, will not work for you. Now, how can I impose a time scale? So here I've given you two examples, two ways in which you can impose a length scale. Is this clear? Any questions here? Any questions? Okay, so now if we have to impose a time scale, how would I impose a time scale? Now maybe you can think and you can suggest. Yes, how would I do that? Yeah, so a case that we are going to consider next, where I'm oscillating certain things. Right, so you can see that I'm now imposing a time scale, which is essentially the frequency with which I'm moving. Right, so that's my time scale which is coming from there. What else could be a time scale? Another time scale could be, I said that at time t is equal to 0, so we said that u is equal to 0, at t less than equal to 0 and u is equal to capital U at t greater than 0. Right? That's the sort of the solution. That's the thing that we said. So instead of doing it like this, if now we say that this has a velocity u1 for time t greater than 0 and less than t1, and then it is going to have some other velocity for time greater than t1, which is a velocity u2. Right? So I say that I have moved it suddenly. I keep it at that velocity level for some time, velocity value, and then I change the velocity value. And then you can see I can keep on doing this if I can do it multiple steps. I have done one step, I can do infinite number of such steps. Okay, so then you can see that I'm now imposing, my solution has to satisfy now that whatever solution I get should be equal to the velocity u1, should give me the velocity u1 at the wall. Okay, and then after time t is equal to t1, it should now give me at the wall, again the solution should automatically change itself and say that at time for any value of t greater than t1 that I take, put in that solution, okay, at the wall I should get u2, only then is the right solution, correct? The solution has to necessarily satisfy the boundary condition, right? Is this clear, understood? So you can see that these are two simple ways in which I can impose a time scale in the problem. Okay, any questions here? So what does it mean now? That in our problem, coming to the problem that we are looking at, what are we doing? Do we expect a similarity solution to apply? The answer is no. We have already explained to you that we are imposing a time scale. We are not imposing a length scale in the problem, but we are imposing a time scale in the problem. Okay, and therefore this is not going to work. And what does it mean? It means that we will not have any combination like this. You will indeed be a function of both y and t separately. Okay. Now think of what will I get in with respect to, so that is sort of understood now, right? Now, but let us just think of, if I just oscillate a plate in the flow, what do I expect to get? So think of it intuitively. What do I expect to get? What should the fluid do? It should also oscillate. Okay. Now, what will be the difference? So will it oscillate at the same frequency, same amplitude? What should be the same between the plate and wherever I'm looking at my fluid? There should be a phase lag. That's very correct. But what should be the same? Should anything be same? The frequency should be the same. Okay. Amplitude can vary, or amplitude would vary. Why would amplitude vary? It is clear that, okay, at the surface, the amplitude will be u, okay, whereas very far away, amplitude is essentially 0, right? Yes, these are all okay. So these are all under the conditions of the flow is laminar. That's right. And where is this? Okay, by the way, where is it coming in our analysis? We have not. Where are we sort of saying that the flow is not turbulent? In our case, the channel flow problem that we did, for example, channel flow also we also can get turbulent channel flows. So in our analysis, what would change readily? Let us say, solution would change. Of course, the governing equation, the way we have simplified, what would change there? There will be a time temporal term. Okay, okay, that is partially correct. We will see that there is something which we'll call the stationary flow, where the time dependence will go away still. Okay, that's a little bit of an advanced concept, so we'll have to wait for that. But anything else? Yes. Kinematic viscosity, it does not really change. Really, that's a fluid property. Okay, it's not a property of the flow. So kinematic viscosity does not change. No mixing, but how do I enforce that? What does it mean? Mixing is an outcome like of the flow being turbulent. Fluids will tend to mix more. Where one place where, which is not, I can understand, it's not very transparent to you, the flow will always, turbulent flows are always three-dimensional. Okay, so 2D analysis you cannot do. Okay, so you have to keep the third term. Of course, in the mean, it could be, the mean flow could be like two-dimensional, but that is a little bit, again, a concept that we'll have to keep it as for the, we can come back, revisit this point when we're talking about turbulent flows. But turbulent flows are always three-dimensional and always unsteady, like what was mentioned. So so we are always going to talk about incompressible flow and Newtonian fluid. It is given, but incompressible flows can still be turbulent. So we are also assuming that these are, we are working in the laminar regime. Okay, so now we have already said that we will be looking for a solution. That ultimately the fluid will start oscillating and would have a frequency which is the same as whatever is the imposed frequency. The amplitude could vary, and the phase could be very different. So this is what we would intuitively expect, which is absolutely fine. But we have to also understand that there is a transient part to it. Okay, so I hope you understand, you recall from so many other discussions in other places that there is a transient. So solution will initially have transients, and that transients will happen because the flow is initially static and it has to attain whatever is the final velocity that it is attaining. Okay, and that final velocity is not a constant, that is also a function of time. So it is going from 0 to that value in some manner, right? Is this understood? So that this transient part, we are going to say that right now we are not interested in that. So we are only interested in after a certain time, after I have started doing shaking the plate, what solution do I see? Not immediately after. Okay, so whatever we are going to do, so then we are sort of removing the transient. We are not trying to solve for the transient. We can solve for the transient part. Same governing equation is going to be applicable and everything. Is that we don't want to, we are not interested in trying to solve for that transient part. Is this understood? Okay, so that's what we are going to do now. So, so that means that in some sense I don't have to prescribe. So how do I solve this equation? It requires some initial condition and it requires some boundary condition, two boundary conditions. So we can say that I don't have to prescribe any initial condition because I am not looking at time which is just after the flow started. At time t is equal to 0, I'm going to look at sufficiently far. What is sufficiently far? I have not even defined that. Okay, one has to rigorously find out whether what is that time beyond which the solution is applicable. We are not defining that, but we know intuitively that there will be some time after which the flow will simply be oscillating. So I'm not going to prescribe this. Now boundary conditions. So how many boundary conditions do I need? Two boundary conditions, because you can see derivative, second derivative of u along y direction. And what are those boundary conditions? U at y is equal to 0 and time t, all time, here it is greater than 0 if you want, you can say it. Okay, all time, maybe just leave it like that because we have not really defining t is equal to 0, etc. So what is it that we expect to get? U cos omega t, u cos omega t, and this is what we are getting from the no slip boundary condition. Okay, whatever is the velocity of the plate, the same should be the velocity of the fluid next to the plate. Okay, so that's the condition that we are imposing here. So that's my first condition. Now what is the second condition I should impose? So at very far away, what is happening? Yeah, amplitude is 0, but that is oscillating with time. Oscillating is 0 amplitude means it is constant. I don't know. So maybe, see, in such cases, there is a condition that we are going to write, which looks sometimes when you see it first time, it is a little bit strange, but is actually a very powerful condition. And that condition is that at u, as y tends to infinity, it is bounded. We are simply saying that it is bounded. Okay, velocity cannot become infinite. Okay, I am just giving it as a finite velocity here. Somewhere else, it could be anything. I am only saying that it is bounded. Okay, is this clear? So we have defined the problem now, and we are going to try to solve this equation. Okay, any questions before starting with whatever we have said till now? Yes. Yeah, that's what I'm saying. The first time when you look at it, it looks a very restricted, but you will find that it is actually a very powerful condition. Bounded can actually help you get rid of three different functions, three different constants in just from this bounded condition. Okay, and what it means is, like, let us say, if I just to give you some practical sort of a thing, if you see a ln x, x is at x is equal to 0, what happens? What is ln x at x is equal to 0? Yeah, it's in getting growing in, this is growing in an infinite manner to a minus infinity. So just remove the coefficient. There's a coefficient here, remove that, 0. Okay, there is an exponential function, exponential xt, whatever, at or ax, x tends to infinity. Remove this, the coefficients here. This term is also gone. So you can see that one condition may let you get rid of two different coefficients. It's a very powerful condition. It's a far more powerful condition than saying that although it may look like, oh, it's very vague, but it's actually very powerful. Whereas if you say 0, then okay, you'll have to see what exactly it means. Maybe there will be certain things, some other terms in this question, which will in total will make it 0. So whereas here we cannot make it 0. I mean, things like that. Okay. So okay. So we are okay. Any other question before starting? So instead of trying to solve it, we are going to take some sort of a shortcut, and we are going to say that we are going to seek solution of the form that it is exponential of I omega t. So what is exponential of I omega t? We will come to the right to the other part. But what is exponential of I omega t? I is the imaginary number. Imaginary I is equal to square root of minus 1 iota, as it is sometimes called. Okay, square root of minus 1. So what is the property of this exponential of I omega t? It is equal to cos omega t plus I sin omega t. Okay, so you can see that we have to look for something cos omega t. Okay, so this cos omega t is built in, and I'm also adding another term. Okay, and this I'm adding because we will see that it can help us find the phase. Okay, because the solution is not going to be just cos omega t. It can, as we said, there would be a phase, and this term, writing it out in this manner, will help us pick that phase. Okay, so ultimately, so that is what. So this is essentially taking care of the cos part, and then there is going to be some function of y that I'm going to have. Okay, so I'm seeking that u is of this form. This is understood. So this we are getting because it has the cos omega t term. Okay, and as we said, as far as time goes, that's the only thing which is happening. Okay, it's just oscillating, as we have intuitively said, it's just oscillating with respect to time, but the amplitude can vary. So the amplitude part is now there in this f term. Okay, and ultimately you can say I'm taking the real part of it. I am not writing it down, but like for the first time, maybe you can say real part of this is what I'm interested in. Okay. Again, any questions here? So if I see that I'm not going to carry this real part forward every time, I'm just writing it once. So if this is the solution, it should satisfy this governing equation, which is obvious. So that means I'm going to say I substitute it here. What do I get? F is not a differential. The left hand side will give me an I omega exponential of I omega t and multiplied by f. And what do I get from the right hand side? Second derivative of f double prime. Let me just write it out as d to f dy2 and exponential of I omega t. So you can see now the advantage of writing out in terms of I omega t. It has made life so simple. Okay, you can see simply I omega t. Sorry, this is, yeah, I omega is not an argument of this. Maybe I can write it here. I omega times f times exponential of I omega t. So you can see exponential I omega t cancels on both the sides, and I have a very simple looking governing equation, a second order ODE that I need to solve. So you can see that what we need is the equation is minus I omega upon nu times f is equal to 0. Right? So what is the solution of this equation? So what type of an equation is this? Okay, this is just an imaginary number. It's an imaginary coefficient, but otherwise it's a constant coefficient, right? And what is how do we solve this constant coefficient type of an equation? We simply say that f, it is going to be exponential of, let us say, ay or alpha y. Right? You seek solution of this form. Seek solution of this form. And I'm going to now substitute in here. I get alpha square times exponential of alpha y minus I omega upon nu times exponential of alpha y is equal to 0, which gives me that these are 0, these are gone, and therefore alpha is equal to square root of this thing here with a plus minus. I should have two coefficients, so I should now put plus minus in there. Correct? So you can see that the solution is relatively straightforward once you know this is in some sense the key step. Okay, once you understand this step, after that everything just follows after that. So what is the square root of I? 1 upon times omega upon nu square root of this, and plus minus is what I would have. Okay, so what is my solution that I get? My u or my my f is equal to, let us say, a times exponential of alpha 1 y let us say a1 here and a2 here, exponential of alpha 2y. Everybody with me? Okay. And what is my alpha 1 and alpha 2? So alpha 1 is equal to, I can just take 1 plus I upon square root of 2, and alpha 2 is equal to minus 1 plus I upon square root of 2 times square root of omega by nu square root of this. Okay, so these are my two things that I would have. Now what can I say about A1 and A2? Now I have to apply. So how do I evaluate my A1 and A2? By applying the boundary conditions which are here. So if I apply the boundary conditions, and again bounded condition is very easy to apply it first. Okay, so what does bounded condition tell you? As y tends to infinity, what happens? So this has a positive, everything is positive here, and this has some negative. Okay, so this, as y tends to infinity, this exponential term is going to grow unbounded, right? And which we cannot allow. So that means that we will have to set a1 is equal to 0. So a1 is equal to 0, from bounded condition, from boundedness of the solution. So A1 is gone, and I'm left with A2. And what is A2? We can see that it will work out as simply U. Okay, so but because you have to again take the real part of this, you have to take the real part of it, because that's the part which is coming in your F. If you take that, you will find that simply U. Okay, because again there are cos and sine terms, and the other terms are not going to be important for you. So okay, so finally what do I get is the solution becomes U is equal to capital U exponential of I omega t exponential of minus of 1 plus I upon square root of 2 times nu upon alpha or omega by nu. So this is what I get. This is the solution, and now I have to take the real part. And now I have everything. Now I should take the real part of this and say that that's my U. U is equal to a real part of all this. So what is the real part of this? How do I take that? Okay, again, you can now add up these two. The exponents will add up. Okay, and then you look at the real part, and we divide it again in cos and sine. The omega part and the real part can be just taken out. So here, for example, I can just say that this is equal to U times exponential. I will just do maybe one or two steps. If I just look at the exponential part, this is plus or minus I upon square root of 2 times omega upon mu square root of this times y, of course. This is y here. So this is what I get from the exponent, and then the other exponent, which is real, is minus 1 upon square root of 2 omega upon mu times y. So I hope I have not made any mistake here. Right? So then that you can see that U times this, which is all real, is now my amplitude, and this is where I will get cos and sine term, and I have to just keep the cos part or the real part of that. So I can just give you the final answer. So I finally get that U is equal to capital U exponential of minus y times omega upon square root of 2 nu times cos omega t minus y times omega upon 2 nu square root of this, and a product of these two terms is. So this part just gives me this cos part, and this other part is as before. Okay. And as we said, how do we interpret the solution? You can see that as you keep going further and further away from y at larger y, this is my the amplitude part. The amplitude is decreasing, as you were saying. Somebody was saying that amplitude is becoming 0 at y tending to infinity. Okay, so that's what the amplitude, I mean, this is also what the solution is giving. And the second part is simply looking at the phases, the frequency is preserved here, and you can see that this is the phase term, omega t minus phi. This is like your phi term, and phi depends on where you are in the flow. Okay, so it depends on y, and of course it depends on diffusivity. which is nu, momentum diffusivity nu. It does depend on what is the frequency at which you're oscillating things. Okay? Yeah, that's what we said, that if you just take the cos, you will not get the phase term, because it's not just happening with the same phase throughout. Okay, so you are forcing yourself to say that I'm only going to say look for a solution which is cos omega t multiplied by some amplitude. Okay, and you can see very clearly that that is not the final solution. Okay, because the final solution is dependent on, as we said, intuitively, it should also change the phase. The phase part you can only get by looking at the I sin omega t term. So you go from a real plane to a complex plane, work there, and then you take the real part of it and come back to the real plane. Okay. So I mean, you can do it without the imaginary part. You can do it purely in the real with the real variables. But this is a much simpler way of looking at the solution. Okay. The only sort of difficulty is initially when think of it. But as I'm trying to sort of explain to you, the phase you will not get, because you can think of that cos omega t plus I sin omega t. The I sin omega t is ultimately going to help you take care of the sign of the phase part. So you are trying to introduce it through that term. Through that term is where the phase information will get captured by you. And that's what happens later on. So you can see that this is a Stokes second problem. Again, we have physically it's not very difficult to understand, and it just gives you in the process we could sort of understand that where can we apply similarity, where can we not apply similarity. Okay, that comes out very clearly from this problem. Okay, and I would not say that this method is very nice or elegant or whatever it may be, but more important thing is to just be able to physically feel the problem. Okay, that how how does the frequency propagate in the flow, let us say. Okay, any questions here? So if not, we will move on to another interesting problem. Rotating cylinders. So let us say we have two cylinders, very long, and we keep two of them. So let us say we have one cylinder, and then we have another cylinder. So these cylinders are concentric, and let us say we rotate these cylinders. So let us say this has a radius of R1, the other one has a radius of R2. I rotate the inner one with velocity omega 1, the outer one is rotated with velocity omega 2. The fluid is sandwiched between these two fluids, between these two cylinders, and our interest is in figuring out how does the velocity look like till again the flow remains laminar. Okay, this is a flow which has been extensively studied. Okay, and extensively studied because it can exhibit all sort of very interesting instabilities. Okay, so this is what we are going to look at. So rotating and cylinders are long. So we assume that cylinders are long. You're looking at long cylinders. So how does it help us? By assuming that the cylinders are long. You have to be louder, please. Dou by dou z is equal to 0. Okay. Basically, there are no end effects. The cylinders are so long that I am essentially somewhere in the middle, and I don't have to worry about whatever is happening at the ends. We can also explicitly write out we are in the laminar regime, laminar steady steady sort of a regime. Yeah, so in some sense, when you say the flow is steady, turbulence is already out. Okay. So any simplifying thing, so you can see that I'm going to be able to. So what is the coordinate system we are going to work in? Cylindrical coordinates. What are the important things here is r and theta. So I can work with r theta z by assuming that, by assuming what? By assuming that the cylinders are long, we have gotten rid of any z dependence. Okay. So, okay, any simplification before even getting started with this problem? Any simplification that we can make? Anything that we know from the problem setup itself that is going to be applicable to us? Axisymmetric. Very good. And what does it mean? No variation in theta. That's very good. So how do I write down this condition? Dou by dou theta is equal to 0. Anything which is here is 0. Okay, and this is a very powerful condition that we have, that there is no derivative along the theta direction. We are not saying that there is no quantity along the theta direction. We are only saying that there is no variation of that quantity in the theta direction. So the gradient of that quantity in theta is equal to 0. So we are going to start out by writing the governing equation. So this is probably the first time we are writing out Navier-Stokes in cylindrical coordinates, NS equations in cylindrical coordinates. And what I would suggest is that you write it. We already have said that there is a cheat sheet that you can bring in. So in that cheat sheet, you can write out, or you should write the Navier-Stokes in whatever coordinate system you want. Definitely in the cylindrical coordinate system, you should have it with you. Okay, and don't just copy it from here. Copy it from a book so that you are. I mean, there are no mistakes in writing it out. So 1 upon r. We are starting off with our continuity equation. U r okay, by the way, before we get to the solution, which velocity components are going to be intuitively you think would be important here? So what are the velocity components first? U r and U theta. Okay, so here we are going to use with a subscript so that it's clear that we're talking about velocity either in the radial direction or in the tangential direction, theta. Okay, so U r or U theta is what we will write. And so which one do you think would be important here? U r or U theta? U r is the velocity. U r is the velocity which is along the radial direction. Which one is the radial direction? So if I look at any point here, let us use a different color. So these are the two directions. What direction is this? This is the r direction and this is the theta direction, correct? Here if I look at it, these are the two directions. What is this direction? Which direction is this? R direction, and this is my theta direction, right? So what do you expect to get? Is the flow is rotating around, right? So it's a U theta that I have, okay, and U theta is the main component. I don't know anything about U r, but I know that U theta should be very important here, okay. So things are varying in the r direction, that is for sure. Things are not varying the theta direction, okay, but the main velocity component that we have is along the theta direction. Yes. How do we constitutive relationship? Okay, so that's a very interesting question. So the question that is being asked is how do we take the of the constitutive equations. See, one thing is that the way we have derived it in Cartesian coordinates. Now, once you have the equation in one coordinate system, you can use the simple mathematical way of transforming the equations from any coordinate system to any other coordinate system. Okay, so then you don't have to go back to your physics. You just say, I'm going to use math from here. I know that if this is my equations, and in this equation, this is how I will transform these equations. I just transform it using it without any going back to my. So that's how I would look at it. But of course, one can go to your drive an equivalent of everything in cylindrical coordinates or spherical coordinates or any other coordinate system that you're interested in. Okay, that's also very much possible. But the first approach is what I would take. At least I prefer to take, let us say. Okay, now when we go to the r and theta, so I'm not going to write out any uz terms. And I'm going to get rid of the unsteady terms here as well. U r. So I know these equations are somewhat tedious to write down and work with. So one example I wanted to take with you so that you know how to handle this form of the equation as well. So this is my r momentum equation. Okay, so these are the equations that we have. Now, when you just whenever we write out these equations, at least what I would do, and I think that's a good idea, good practice, that you can check the equation whether they are dimensionally consistent or not. Okay, and how do I check that very quickly? You know that what are the dimensions of u theta? What is the dimension of let us say theta? Theta is dimensionless. R has dimensions of meters. Okay, so if I take a derivative of any quantity with respect to theta, I'm missing a dimension, and something else which is a dimension with the derivative with respect to r. Okay, so then one length unit is missing, so it has to be divided by r somewhere. Okay, so that is one sort of simple thing that you can remember, that that's one thing. And of course, when you look at the dimensions of u theta and ur, what are the dimensions? Don't say u theta is dimensionless just because theta is dimensionless. Okay, u theta and ur are both velocity components in different directions. Okay, so they are going to have both dimensions of meter per second, or units of meters per second. So if I look at this equation, for example, where can we? So you can see this is meters. I mean, this is in velocity. You can think of this velocity, and this is r into a length scale. And you can see you are dividing it by two length scales here. So it's velocity by length scale. And same thing you can see, theta is dimensionless and it's velocity by length scale here. So at least dimensionally, at least this is okay. Here we know the left hand side of the Navier-Stokes equation has velocity times velocity gradient. So it is velocity square upon meters, or length scale divided by length scale. So that's what you should have here as well, which is what you see here. Okay, velocity square divided by length scale. Okay, which is also what you see here, velocity square by length scale. Right hand side has, of course, it is all dimensionally consistent, but pressure divided by density, or pressure gradient divided by density. So this is fine. Nu is there, and then this is whatever the dimensions here. So if I look at something, it is velocity by length square, and therefore I should also have. So that is also same here. It is also same here, and it is this term. We'll have to see how many terms you are actually dividing it 3 times by r. You are multiplying it, so but you are also multiplying it by 1. So you are only having velocity by length square again. Okay, so just one again, as we said, it's a good idea to again. So that will quickly tell you that if there is a obvious typo in your equation, it will quickly tell you whether that is there or not. Similarly, you can do it velocity square upon length, velocity square upon length, velocity square upon length. And this is pressure. You can see immediately, if you had written with theta, not put this r, you know that you have an issue. Okay, this r has to be there, only then it will become dimensionally consistent. Here it is velocity upon r square. So velocity upon r square, velocity upon r square, and this is again velocity into r divided by 3 times or r cubed. So it's again, so this is at least dimensionally equations are okay. Does not mean that it is correct, but it is at least dimensionally not inconsistent. That's all we can say. Okay, so the first thing that we are going to do is to start using our condition of axisymmetry, which is that derivative of anything with respect to theta is equal to 0. So that's a very powerful condition, and that allows us to immediately, and we always start off with the continuity equation. We have already said that all these things will not change. So if you go to the continuity equation, you can see that this term is 0. Okay, and that tells me that this term is equal to 0. Okay, and if this term is equal to 0, I can readily integrate this. Okay, 1 by r is gone, and then that means derivative of r times ur with respect to r is equal to 0. And what does it mean? R times ur is equal to constant. Okay, so this integrating it. So continuity gives me r times ur is equal to constant. Correct? Now, what is the value of that constant? Again, you can go to apply the boundary conditions. At the boundary, what is the value of ur at the boundary? 0. Why? No penetration. No penetration. Here it is perpendicular to the direction of the wall. So you have to look at not slip, but penetration. Okay, so this is a no penetration boundary condition. So it gives you that UR is equal to 0 at the wall, at cylinder walls, and therefore that means this constant is 0, and therefore UR is equal to 0 throughout. Implies that constant is 0, and which implies that UR is equal to 0 throughout. Right? Everybody with me? So now what is the next equation that we should solve? R momentum equation, where the action is in the theta direction, so we should solve it at the end. Correct? Same thing we are going to do here. So which of these two are the R momentum and which one is theta momentum? So here you will say UR, U theta, everything is looking very similar. So at least what I do is look at pressure term. Okay, wherever is a pressure gradient term, it tells you whether it is looking at the R direction. Pressure gradient is along the I direction, that's my R momentum equation. The theta direction is the theta momentum equation. So that's a very quick, you don't have any confusion if you do that way. Okay, so here, this is along the R direction, so this is my R momentum equation. Okay, so UR is now 0, so all this is 0, this is 0, this is 0. All this is 0, this is 0, this is 0. Okay, and this is 0 because of axis symmetry. So you can see that everything is 0 other than these two terms here. So only thing which remains, so the R momentum equation implies that minus U theta square upon R is equal to minus 1 upon rho times dou P dou R. Of course, I can now get rid of the minus sign, and this is what I get. So you can see that unlike the previous case, there was no gradient along the lateral direction. There is a pressure gradient along the lateral direction. And why is that? What is this term? This is centrifugal force sitting here. Okay, so you can see that pressure gradient will set up to balance the centrifugal force that has been created because of the rotation. Correct? And it tells you that you can directly integrate this equation. Okay, and you can see how the pressure is varying along the as a function of R. Pressure is not varying with respect to theta because of axis symmetry condition. We already said that, but pressure can still vary along with R, and that will vary like what we have seen here. Okay, and it tells us, in fact, we can pause here and say that although we are doing it for this particular problem, we can take any streamlines which are bending. Okay, anytime the streamline is bending, it is telling us that whether it all reduces to exactly this or not, it is immaterial. But it tells us that pressure has to vary in the radial direction. This is my radial direction, and pressure has to vary in the radial direction. Okay, understood? So it is already giving you, so the moment there is the streamline curve, you know that there is a pressure which is there in that lateral direction. Okay, so don't forget this. So this is a very simple and an important conclusion that we are getting from this R momentum equation here. And we are not trying to integrate it. You can integrate it and get it, the exact solution. So now we come to the theta momentum equation, which is our main equation. So the theta momentum equation, help me simplify. First term, First term, 0, y, u 0. Second term, axis symmetry, 0. Third term, u are 0. So when, I would again urge you when you do this, it will help you for the exam. Okay, you set the right thing to 0. Okay, So if you just show me that UR is 0 and therefore this term I'm dropping, it makes more sense other than putting a, so if you can be just a little bit more careful in writing it out, why you are setting it as 0, okay. So you can see that in this itself we are saying that I'm taking this derivative and that derivative is 0, okay. Now here, so right hand side, first term 0, why? Axis symmetry. This term non-zero, agreed. This term 0, axis symmetry. This term 0, axis symmetry. This term non-zero. So the theta momentum equation reduces to left hand side is 0, right hand side is nu times 1 upon r times dou by dou r of r dou u theta dou r minus u theta on r square. Okay, everybody with me? So this is the equation that we need to solve, and you can see that this is a single equation. In fact, this is an ODE, not a PDE, okay, because u theta is only a function of r. It's not a function of theta, it's not a function of t, it's not a function of z. So it's only a function of r. Okay, so we can change all these partial derivatives to total derivatives, and we can start solving it there. And of course, you can get rid of nu altogether. Okay, any questions? So this is the problem setup, and we will now solve it. Maybe before that, we can prescribe the boundary conditions as well. Boundary conditions are relatively straightforward. As you can see, although the equations are very, very tedious in this case, okay, why this is a nice problem to look at is because you started off with such a complicated looking equation. Here we have not even put the z term. You can even put the z terms in there. You can also put the unsteady term, which I have also deliberately removed, just to keep, just to reduce or remove a few terms from the equation. Okay, so but you can see that it reduces to a very, very simple solutions or some simple things. UR is equal to 0, that's what you get from continuity. From the R momentum equation, this is what you get, and from the theta momentum equation, this is what you get. Okay, okay, questions here? So maybe we will just simplify this equation, the theta momentum equation. I don't have to now keep saying that's a theta momentum equation. We know that that's the only equation that is meaningful to be carried forward and solved. So it becomes dr2 plus 1 upon r du theta dr minus u theta upon r square is equal to 0. So this is what I would get from here. I don't have to carry nu forward. Okay, and you can see this is a second order ODE. I need to prescribe two boundary conditions. So before even trying to solve it, let us write down the boundary conditions. What are the boundary conditions? You can look here. So at r is equal to r1, we have, let me just, yeah, so what is my u theta at, what is my u theta? Omega 1 r1, and at r is equal to r2, my u theta is equal to omega 2 r2. So as we said, very simple conditions that we can put in here. Now, how do I solve this equation? Yeah, so this is a very simple equation again. You remember how we solve it? Sure. So what is the solution? R to the power of n. So assume that this has a solution of r to the power of that n here. Now what is the value of n? You substitute that into the equation. So seek solution of the form u theta is equal to r to the power of n. So I get, upon substituting, so putting r to the power of n in the governing equation, we get n times n minus 1 r to the power of n minus 2 plus n times r to the power of n minus 2 minus r to the power of n minus 2 is equal to 0. And why the solution works? Because r to the power of n minus 2 cancels away, and I'm left with n square minus n plus n minus 1 is equal to 0. So I get n is equal to plus minus 1. Okay, so that means that my solution u theta is r to the power of 1 plus 1 gives me r, and r to the power of minus 1 gives me 1 by r, and I have to take a linear combination of these two. A plus b upon r is the solution that I would have. Okay? Any questions here? Any questions here? So I can now solve for A and B using the two boundary conditions. So I'll just write down, use boundary conditions to solve, to obtain A as omega 2 r2 square minus omega 1 r1 square divided by r2 square minus r1 square. By the way, you can also do dimensional analysis here as well. Okay, and you should do it at every stage. This is a dimensional equation. So dimension of A should be velocity divided by length scale. Okay, and dimension of B should be velocity times length scale. Okay, so something that you can keep an eye on when you write out all these things. Make sure that again you are dimensionally writing out things which are dimensionally consistent. B is equal to omega 1 minus omega 2. So I will just leave it as a homework, as a small homework. Okay, just obtain these expression. Not difficult at all, but at least it will give you some work, some reason for you to open your notes and look at it. Okay, so this is the solution that you would get. These are the two coefficients that you would get for A and B. Reasonably involved here, but reasonably simple otherwise. And you will get u theta as r2 square upon r2 square minus r1 square times omega 2 minus omega 1 r1 square upon r2 square times r plus r1 square upon r times omega 1 minus omega 2. not written it very nicely, neatly, but I hope you can read omega 1 minus omega 2. Maybe I'll just try to write it again. Okay, plus r1 square upon small r times omega 1 minus omega 2. So this plus this term here. Okay, so this is simple enough. Any questions here? There is only one. No, there are two cylinders here now. Yeah, so right now is this clear first of all? So, okay, I will answer your question in a minute. Any questions here on this solution, whatever we have done? So now we are interested in looking at a few special cases. So what are the special cases that we can drive? Okay. Okay. So what are the special cases one can think of from here? Omega 1 is 0, omega 2 is 0. That is straightforward. One can get it from the solution that we have. Anything else? Anything more interesting than that? Opposite direction also you can look at. Okay, so let us think of R1 tends to 0 or is equal to 0. So what does it mean? My inner cylinder has vanished. There is no inner cylinder. There is only one cylinder which is rotating. Okay. So what is the solution I would get? Okay, so by the way, if you have to solve this problem, what happens? What is my second boundary condition now? If I have to, I can get it directly from this solution. I'm going to use that. From this solution, I'm going to put R1 is equal to 0 and everything is going to be very well behaved. I can put R1 is equal to 0 here. Okay, but if you started to solve it as only one cylinder problem, then what is the boundary condition that you will put? Governing equation, as you can see, is still the same. U theta is bounded. Again, the boundedness condition is going to be very useful for you. And what does it mean? When you get A plus AR plus B upon R, B has to be 0. Immediately you can say B has to be 0 because B is now no longer, 1 upon R is becoming unbounded at R is equal to 0. And therefore, I will get rid of that term, of the B term. Correct? And that's what you would see from here as well. Okay, if you put R1 is equal to 0, you can see that the second term that we have written is becoming 0, identically 0. Okay, and from here you can simply get the solution is U theta is equal to omega R, omega 2R. Okay, clear? Now, similarly, you can, and so what sort of a solution is this, by the way? This is a solid body rotation. So this is solid body rotation. Okay, and this is very important. We will see that, we will see when you go to vorticity dynamics, we will talk about this more and more of this. Now, what is the second case that we can look at? As R2 tends to infinity. Okay, R2 tends to infinity means that the second cylinder has now vanished. So there is a cylinder which is, in the first case is what is it looking at? It's looking at the flow inside the cylinder. The second one also has a single cylinder, but then we are looking at the flow outside the cylinder in the second case. Right? And you can work out what is the solution that you would get. Again, you can look here now and you can say that I should put A is equal to 0, again boundedness condition. Okay, and that if you see here, you should get this first term to be 0. Okay, from this solution also, and you can show that. Again, leave it as a homework for you to figure out. I will just list down two more or two to three more conditions. You can work out, I would like you to work out the solution for each of these cases. The third case, we can say that both the cylinders are rotating with the same velocity, omega. So work out the solution for this. And comment on what you are getting and why. Fourth case one can think of is I'm going to force this term to be 0 by saying that omega 2 is equal to omega 1 times r1 square upon r2 square. So I have fixed my radius. The radius of cylinders are given to me, but I can change the angular velocity. I have decided to, I can rotate omega 1 with any velocity, but then I do not give any arbitrary velocity to omega 2, but I give it which satisfies this relationship here. Okay, then you can see what happens and why. And fifth case, we can say that R1 is almost equal to R2. R1 is almost equal to R2 means it's a narrow gap, very narrow gap. They are not exactly equal, of course, otherwise there is no fluid region, but they are approximately equal. Okay, so work out the solution for each of these cases, and this will become useful. So now we are, in fact, we are ready to go to vorticity dynamics. This is all we needed. Okay, and this is now we can start looking at rotation of the fluid motion, which is essentially going to be like a vortex. So we are sort of ready. This problem readies us to go in that direction. Okay, so this is where we will stop. Please do this few very simple limiting cases. Okay, before you come to the class next time.